Let me start with a simple question. We all use tools like ChatGPT, DALL, and Copilot every day. But in interviews, the real question is not whether we can use them. It's whether we understand how these systems actually work. Generative AI is not just another AI feature. It represents a major shift in how a modern software and intelligence systems are built. Generative AI refers to AI systems that can create entirely new content such as text, images, audio, video, or even code by learning patterns from large datasets. Generative AI has rapidly moved from research labs into real-world production systems. Today, it is used in software development, data analysis, healthcare, finance, marketing, customer support, and even in research. Because of this, companies are no longer looking only for people who can use AI tools. They want professionals who understand the architecture, training, and limitation of these models. In interviews, generative AI questions are used to test more than surface-level knowledge. Interviewers evaluate whether a candidate understands core machine learning fundamentals, modern architectures like transformers, and how AI systems are developed and evaluated in real-world scenarios. Nowadays, even non-AI roles are now expected to have at least a conceptual understanding of generative AI systems. Now, before we get started into the questions, if you're interested in gaining in-depth knowledge about generative AI and understanding how tools like ChatGPT, VO, editing tools, etc. work, then I have divided all the important questions into 3 levels. The easy level focuses on the fundamentals and core concepts. The mid-level dives into how generative AI model works internally, including GANs, VAEs, diffusion models, and LLMs. The hard level focuses on advanced topics and production systems such as evaluations, RAG architecture, and scalability. With that in mind, let's get started. Let's start with easy level question and answers. The first question is, what is generative AI? Now, generative AI is a category of artificial intelligence that focuses on creating new content such as text, images, audio, video, or even code. Unlike traditional AI systems that mainly classify data or make predictions, generative AI learns the underlying patterns and probability distribution of training data. Using this knowledge, it can generate original and previously unseen outputs that resemble human-created content. Popular examples include ChatGPT for text generation, DALL and Stable Diffusion for image generation, and Claude for conversational tasks. Generative AI is widely used in chatbots, content generation, image generation, and code assistance, making it a key technology in modern AI systems. The second question is, how is generative AI different from traditional AI? Traditional AI, also known as discriminative AI, focuses on prediction and classification tasks. It learns the probability of an output given in an input, such as identifying spam emails or detecting fraud. Its main goal is to separate or classify data using learned decision boundaries. Generative AI, on the other hand, learns the entire data distribution and focuses on generating new data rather than predicting labels. It can create text, images, audio, or video from prompts or noise. In simple terms, traditional AI answers what something is, while generative AI focuses on creating something new like it. Let's move on to the third question, which is, what are key components of generative AI models? Generative AI models are built using several core components that work together. The process starts with input such as text or images. This input is converted into numerical form using embeddings, which captures meaning. This attention mechanism helps the model focus on most relevant parts of the input. Next is the hidden layers, perform complex transformation, and learn patterns from data. Finally, the output layer generates the final results such as text or images. This pipeline, which is input, embedding, attention, hidden layer, and output, enables generative AI models to produce meaningful, coherent, and context-aware content. The next question is, can you explain neural networks in simple terms? Neural networks are inspired by the structure of human brain and are made up of interconnected units called neurons. Each neuron receives input, performs a calculation, and passes the results forward. These neurons are organized into layers including input, hidden layers, and even output layers. The connection between the neurons have weight, which is adjusting during training to minimize errors. Learning happens when the network updates these weights based on feedback. Activation function allows the network to learn complex nonlinear patterns. In simple terms, a neural network learns by strengthening or weakening connections until it produces accurate results. The next question is, what is a transformer model? A transformer is a neural network architecture introduced in 2017 that revolutionized AI, especially in natural language processing. Its core concept is self-attention, which allows the model to focus on different parts of the input simultaneously. Unlike older models like NNS, transformers process entire sequence in parallel, making them faster and more efficient. They use multi-head attention to capture multiple relationships in data and position coding to understand order. Because of these features, transformers are highly scalable and powerful. Modern models such as GPT and Claude are built using transformer architectures. The next question is, what is the difference between machine learning and generative AI? Machine learning is a broad field of AI that focuses on learning patterns from data to make predictions or decisions. It is commonly used in tasks like classification, regression, and recommendation systems. Generative AI is a subset of machine learning with a more specific goal, which is generating new content such as text, images, or audio. While traditional ML models predict outcomes, generative AI models create original outputs based on learned patterns. All generative AI models rely on machine learning techniques, but not all machine learning models are generative. This distinction explains why generative AI is especially useful for creativity and conversational applications. The next question is, what are the real-world applications of generative AI? Generative AI is widely used across various industries due to ability to create and automate content. In text-based application, it is used for writing, translation, summarization, and chatbots. In image generation, tools like DALL and Stable Diffusion help create artwork and designs. In software development, generative AI assists with code generation and debugging. In healthcare, it supports drug discovery and medical report generation. The finance sector uses it for automated reports and fraud analysis. Additionally, generative AI plays a major role in marketing, social media content creation, and customer support through intelligent chatbots. The next question is, define natural language processing, which is NLP. Now, natural language processing or NLP is a branch of artificial intelligence that enables machines to understand, interpret, and generate human language. Since human language is unstructured and complex, NLP techniques help convert text or speech into forms that machines can process. NLP includes tasks such as text classification, sentiment analysis, translation summarization, and question answering. It is widely used in chatbots, voice assistants, search engines, and recommendation systems. By combining linguistic, machine learning, and deep learning, NLP allows machines to interact with humans in a more natural and meaningful way. The next question is, what is deep learning and its relationship to AI? Deep learning is a subset of machine learning that uses neural networks with multiple hidden layers to learn complex patterns from data. It is a part of broader field of artificial intelligence. Unlike traditional ML, deep learning performs automatic feature extraction, reducing the need for manual feature engineering. The layered structure allows models to learn hierarchical representation from simple features to complex concepts. Deep learning scales well with large datasets and high computational power, which is why it dominates fields like computer vision, natural language processing, and speech recognition. Most modern AI systems rely heavily on deep learning techniques. Moving on to the next question, which is, what are the main advantages of generative AI models? Generative AI models provide several important advantages. They enable automation by handling tasks such as content creation, coding, and customer support. These models are highly scalable, allowing the generation of large volumes of content without additional manual efforts. Generative AI helps with dependency on human resources. It also supports personalization, create customized content for individual users. Another key benefit is speed, as content can be generated in seconds. Additionally, generative AI offers 24/7 availability, making it ideal for chatbots and customer support systems across industries. Now we'll move into intermediate questions. The next question is, what are GANs, which is Generative Adversarial Networks? GANs are a type of generative AI model made up of two competing neural network. GANs are a type of generative AI model made up of two competing neural networks working in an adversarial setup. The first network, called the generator, creates fake data samples such as images by learning from random noises. The second network is called discriminator, which evaluates whether the generated data is real or fake by comparing it with real training data. Both networks improve iteratively through competition, where the generator tries to fool the discriminator and the discriminator tries to detect fake samples. This adversarial process results in generation of high quality, realistic synthetic data. The next question is, explain how GANs work. GANs work through an iterative training loop involving two neural networks, which is the generator and the discriminator. The discriminator is trained first to disguise between real data samples and fake samples generated by the generator. At the same time, the generator learns to produce data that can fool the discriminator into believing it is real. Both the networks continuously update their weights based on feedback from each other. Over time, this competition improves the performance of both models. Ideally, GANs reach an equilibrium state where the discriminator can no longer reliably tell real and fake data apart. This process enables GANs to generate highly realistic synthetic data. The next question is, what is generator and discriminator in GANs? In generative adversarial network, repeat that. In generative adversarial network, the generator and the discriminator play two opposite but complementary roles. The generator takes random noise as an input and learns to create fake data samples, such as images that resemble real data. Its goal is to generate output realistic enough to fool the discriminator. The discriminator, on the other hand, receives both real data and generated data and learns to classify whether a given sample is real or fake. During the training, both models improve iteratively. The generator produces better sample, the discriminator becomes more accurate. This competition drives GANs to generate highly realistic synthetic data. The next question is, compare diffusion models with GANs. What are the key differences? Diffusion models and GANs are both generative AI techniques, but they differ significantly in how data is generated. Diffusion models create data by gradually removing noise from an initial random signal through multiple denoising steps. The process leads to high realism and greater output diversity through generation is slower due to multiple steps. GANs, in contrast, generate data through an adversarial process between a generator and a discriminator, usually producing results in a single step. GANs are generally faster but may suffer from issues like model collapse, resulting in less diverse outputs. Overall, diffusion models prioritize quality and diversity while GANs is emphasized on speed. The next question is, explain VAEs architecture and loss function. Variational autoencoders or VAEs are generative models that learn a probabilistic latent space to generate new data. The architecture consists of an encoder which maps input data into latent space represented by mean and variance, and a decoder which represents reconstructed data from a sampled variable. Instead of learning a single latent point, VAEs learn a distribution enabling smooth data generation. The VAE's loss function has two components. Reconstruction loss, which measures how well the output matches the input, and KL divergence, which regularizes the latent space to follow a known distribution, usually a standard normal distribution. Together, these ensure stable training and meaning data generation. The next question is, how do transformers power modern generative AI applications? Transformers power modern generative AI applications through their ability to model context efficiently using self-attention. Self-attention allows it to understand relationships between all parts of the input simultaneously, improving contextual awareness. Transformers also support parallel processing, which enables faster training into interface compared to sequential models. This scalable architecture allows them to handle massive datasets and grow into very large models. Additionally, transformers enables strong generative capability by predicting the next token based on learned context. Because of these advantages, transformers form the foundation of systems like GPT, BERT, and models used for images and speech generation. Next question is, what defines a large language model and its training process? A large language model or LLM is a transformer-based neural network trained on massive amounts of text data to understand, generate, and reason using human language. LLMs learns language by predicting the next token in a sequence, which helps them capture grammar, context, and meaning. The training process begins with tokenization, where the text is converted into tokens, followed by pre-trained on large diverse datasets. After pre-training, models undergo fine-tuning or task-specific or instruction-based data to improve usefulness or safety. After pre-training, models undergo fine-tuning on task-specific or instruction-based data to improve usefulness and safety. Once trained and fine-tuned, the model is deployed as an LLM capable of performing tasks like text generation and question answering. The next question is, name major LLMs and categorize them as proprietary versus open source. Large language models can be broadly categorized into proprietary and open source models based on their availability and licensing. Proprietary LLMs are developed and controlled by companies, and their internal models and training data are not publicly accessible. For example, include OpenAI's GPT 3.5, 4, Google's Gemini, Anthropic Cloud, and even Microsoft Copilot models. These models typically offer strong performance and enterprise support. Open source LLMs on the other hand are publicly available and can be modified or deployed by organizations. For example, it includes Meta's LAMA, Mistral AI's models, Big Science, Bloom, TII's Falcon. Open source models promote transparency, research, and customization. The next question is, how does the attention mechanism work in transformer models? The attention mechanism in a transformer models allows the system to focus on the most relevant parts of the input when generating output. First is input tokens are converted into three vectors called query, Q, key, K, and value V using linear projections. Attention sources are calculated by taking the dot product of the query along with the keys, measuring how strongly tokens are related. These scores are normalized using a softmax function to obtain importance weights. The weights are then applied to the value vectors to produce a weighted sum. This results in context-aware representation, enabling the model to capture long-range dependencies and contextual relationships effectively. The next question is, what is tokenization and why it is critical for LLMs? Tokenization is a process of breaking raw text into similar units called tokens, which may be words, subwords, or characters, so that a large language model can understand and process language. Since LLMs cannot work directly with the raw text, tokenization converts human language into model-referable format. It enables models to handle large and diverse vocabularies efficiently and supports subword understanding such as prefixes, suffixes, and rare words. Tokenization also helps reduce out-of-vocabulary issues, improving generalizations. A well-designed tokenization strategy improves training, efficiency, scalability, and overall model performance, directly impacting the accuracy and quality of generated outputs. Now let's move on to the advanced level GenAI questions. The first question is, what is mode collapse in GANs and what are proven solutions for those? Mode collapse is a common problem in generative adversarial networks where the generator produces limited or identical outputs, failing to capture the fully diversity of real data distribution. This happens even though the discriminator may still be fooled, leading to poor variation in generated. Several proven techniques help address mode collapse. Mini-batch discriminators encourage diversity by allowing the discriminator to compare multiple samples at once. Mastering in GAN, which is WGAN, stabilizes training using better loss function, while WGAN-GP adds gradient penalty for smoother learning. Other solutions include feature matching, unrolled GANs, and spectral normalization, which together improve training stability and output diversity. The next question is, how do you evaluate large language models? And also explain LLM as a judge. Large language models are evaluated using a combination of automatic matrices, human evaluation, and task-specific benchmarks. Automatic matrices measures aspects like accuracy, perplexity, or blue, while human evaluation assesses qualities such as relevance, coherence, helpfulness, and safety. Task-specific benchmarks test performance on standardized datasets across reasoning, language understanding, and generational tasks. One modern evaluation approach is LLM as a judge, where strong, well-aligned LLM is used to evaluate the output of another model. Judging the LLM scores response based on predefined criteria like correctness, clarity, coherence, and safety. This approach improves scalability and consistency while reducing reliance on costly human evaluations. The next question is, what is latent space in generative models and why does it matter? Latent space is a compressed and continuous representation of data learned by generative model where each point encodes meaningful features of the original input instead of working directly with raw data. The model separates this local space to generate new samples. Latent space matters because it enables smooth interpolation. Latent space matters because it enables smooth interpolation between data points, allowing gradual translation in general outputs. It also captures the cinematic structure of data such as style or attributes, supporting control generation. By learning an effective latent space, generative models improve generalization, diversity, and even realism, making them capable of producing new yet coherent samples similar to the training dataset. The next question is, what roles does self-supervised learning play in modern Gen AI? Self-supervised learning plays a foundational role in model generative AI by enabling models to learn from massive amounts of unlabeled data. Instead of relying on manual labeled datasets, the model creates its own training samples, such as predicting the next word or even reconstruction of masked inputs. This approach eliminates the dependency on cost human annotations and allows models to scale to internet-sized datasets. Self-supervised learning helps models learn rich language and visual representations, which are later refined through fine-tuning. It powers the pre-train of large language models and diffusion models, enables effective transfer learning across tasks, and improves overall generation, robustness, and performance in real-world applications. The next question is, explain in context learning, how do LLMs adapt without fine-tuning? In context learning is the ability of large language models to adapt their behavior using examples or instructions provided directly in the prompt without updating model parameters or retraining. Instead of changing weights, the model treats prompt examples as temporary guidelines within the context window. It detects patterns, formats, and instructions from the given context and applies them during the next token prediction. This allows LLMs to perform new tasks such as translation, classification, or even reasoning on the fly. Since no gradient updates or parameters changes occur, the adaptation exists only within the current context. In-context learning makes LLMs highly flexible and capable of handling diverse tasks without explicit fine-tuning. The next question is, when should you use RAG versus fine-tuning for LLM customization? Retrieval augmented generation, which is RAG, and fine-tuning are two different approaches for customizing large language models. RAG should be used when information needs to be up to date or frequently changing, or when a knowledge comes from external documents or databases. It enables factual source-based answers without modifying models' weights and is usually faster and more cost-effective. Fine-tuning, on the other hand, is preferred when you need consistent behavior, tone, or domain-specific adaptations. It is suited when data stable is well accurated and when the model must initialize patterns. In short, RAG focuses on knowledge retrieval while fine-tuning focuses on behavioral learning. The next question is, what is mixture of expert, which is MOE models, and their advantages? Mixture of expert MOE models are a type of neural network architecture that consists of multiple specialized submodels called experts along with a gating network. Instead of activating the entire model for every input, the gating network dynamically selects and activates only small subsets of experts for each input. This makes MOE models highly efficient. One major advantage is scalability, as models can grow very large without proportional. One of the major advantages is scalability, as models can grow very large without a proportional increase in computation. MOE models also reduce inference cost, improve model capacity, and enable specialization across tasks or domains. This design allows better performance while keeping computational cost manageable. The next question is walk through the RLHF process for LLM alignment. Reinforcement learning human feedback, which is RLHF, is a process used to align large language models with human preferences and safety goals. It begins with pre-trained LLM trained on large-scale text data. Next, the model undergoes supervised fine-tuning, which is SFT, using high-quality human return responses. After this, a reward model is trained by having human rank multiple models, outputs based on quality, helpfulness, and safety. Finally, the LLM is optimized using reinforcement learning, commonly with proximal policy optimization, which is PPO, to maximize the reward signal. This process helps produce an alignment model that generates more useful, safe, and human preferred responses. The next question is compare different attention mechanisms and their trade offs. Different attention mechanisms are designed to balance context, understanding, computational cost, and scalability. Full self attention allows every token to attend to all others, providing the best global context and accuracy. But it has high time and memory complexity. Multi head attention ruins the multiple attention heads in parallel to capture diverse relationships, improving representation power at a higher cost. Sparse, sparse attention limits attention to selected tokens. Sparse attention limits attention to selected tokens, making it suitable for long documents but risking missed context. Linear attention approximate attention to reduce complexity, trading more accuracy and efficiency. Cross attention enables interaction between different inputs, such as text and images, at a cost of additional computation. The next question is how would you design a production grade RAG system architecture? A production grade retrieval augmented generation, which is a RAG system, is designed as a modular pipeline for a reliability and scalability. It starts with data sources such as documents, PDFs, or databases, followed by ingestion and chunking to split content into manageable pieces. These chunks are converted into embeddings and stored in a vector based for efficient similarity search. At runtime, a retrieval fetches most of the relevant chunk based on a user query. A prompt builder then combines the retrieved context with the user question before sending it to the LLM. The system returns a grounded, accurate final answer, often with monitoring, logging, and feedback loops for the production. I hope these questions help you crack interviews for your dream designations. If you found this video helpful, don't forget to like, share, and subscribe to Simplilearn for more such content. Until next time, keep learning with Simplilearn.